Okay, I apologize. I'm away from school. My wife is sick, and so I just need to help out at home. We're just going to build off of what we've covered. So here's a typical temperature time graph for water, where temperature is on this axis, time is on this axis. And you know that when you are below 0 degrees, you have a solid. Here you undergo the process where you go from a solid to liquid. We call that melting. Here you have a liquid. Here you go from having a liquid to having a gas. We call that vaporization, boiling. And here we have a gas. The one thing that we've assumed to be true in all these situations thus far is we are at what's called atmospheric pressure. Atmospheric pressure. That's just the pressure that we feel each day. There are some activities I wish I could do with you today, but I can't, and so we'll have to seek to do that another day. But you know from either flying an airplane or traveling to different altitudes that the pressure changes, and we feel that in our ears. So when we go higher, the atmospheric pressure goes down, and when we go to lower environments, the atmospheric pressure goes up. So what that means here is in a particle diagram where we have a gas, the particles have some certain amount of energy and are far apart. If we compress the gas, now what we have, if I compress the gas, is we can force the particles to be closer together. And when that situation happens, then the intermolecular forces are allowed to be more dominant than the kinetic energy. And so we have a liquid situation, whereas we previously had a gas situation, and the only thing that's changed is the pressure. So just a practical example on this would be if you have a gas grill to barbecue, that propane that you buy in a propane tank is what they call LP, which means it's liquefied propane. And that's why you feel it slosh around if you ever are moving one of those tanks. As you open up the valve, you release the pressure, and so the LP goes from being a liquid and then comes out as a gas. But when it's liquid, as I mentioned to you last week, you can get 500 times more the amount of material in the liquid phase than you can in the gas phase. And so you have a much fuller tank when it's liquefied. Alright, if we take the information here, which is at 1 atmosphere, and now we construct another graph for temperature and pressure, now we get a graph that looks like this. Now, the graph like this can throw you a little bit, but the basic premise of the graph holds true. Orient yourself and realize, alright, this is 0 degrees Celsius. Here's 100 degrees Celsius. So, basically, when you're to the left of this, most of the time, you're in the solid phase. When you are between 0 and 100, you're in the liquid phase, and when you're greater than 100, you're in the gas phase. However, it doesn't work that way for everything, because that assumes the pressure is 1 atmosphere, which is atmospheric pressure. So, in normal experiences, below 0 is when it's ice, between 0 and 100 is liquid, greater than 100 is gas. So right along that line, this is what we experience. Now, what this says is if we alter the pressure, so here the pressure is going up, we can have the ice exist at not only 0 degrees, but we can actually get it to be ice at temperatures above 0 degrees. You see how this is above 0 degrees when the pressure is very high. So this is 218 times atmospheric pressure, but I'm sorry, we can liquefy it. I really messed that up, sorry. Notice how we can, at 0 degrees, it can be still water when the pressure is really high. So if we interpolate a point here and we say, okay, this is probably, and this is not linear, but let's say this is 100 atmospheres. Well, at 100 and 0, maybe it's like this. You'd say, oh, okay, it's still water. As the temperature goes down, then it becomes ice. As the temperature goes up, it's a liquid. But notice here, at more than 100 degrees, it's still a liquid. And this is what I referenced on Friday, how when you have a pressure cooker, and the pressure is higher than 1 atmosphere, you can generate temperatures above 100 degrees, and the upshot is you can cook your food faster at a higher pressure. So these graphs, I'm just anticipating some people have an easier time than others understanding them. But if you do the reading and you kind of just try to think about it, you should be able to do the worksheet. Also, if you have questions, I'm pretty sure that a good number of your classmates are going to be able to answer this without too much trouble. So, hopefully that helps. And hopefully I'm back tomorrow and can answer questions. Okay.